So hello everyone and welcome back to a brand new video, and in this video I'll be solving problem D, that is lucky permutation from round 842. So let's move on to the solution and see how we can solve this. But before we move on to the solution, I want to tell you guys about Newton School's coding contest. As you guys know, Newton Schools does this coding contest every month, and this month the name of the contest is Code Rush X, and the prizes are better than ever before. So you can win prizes up to rupees 10 lakhs, and along with this you can win placement opportunities in top product companies. So like if you guys want to play this for fun or you guys want to play this for placements, that is totally up to you. The contest will be on 28th of January. It will start around 9 p.m. and the contest will be 3 hours long. So there will be ample amount of time for you guys to brainstorm and solve good quality problems. So if you guys want to benchmark yourself or just win some placements, this is a very good opportunity. I will leave a link to this contest in the comments and in the description, so you guys can go and sign up from there and show, or you can flex how good you are at problem solving. So now let's move on to the solution. So in the problem, we have been given a permutation of length n, where n can be up to 10 to the power 5. So something like p1, p2, p3, so on up to pn. We can take any two elements of this permutation, pi and pj, and we can swap them, right? And we have to answer the minimum number of swaps that are required such that the resulting permutation should only have one inversion, right? The resulting permutation should only have one inversion. Now what do we mean by inversion? It is just the number of indexes, number of index ij, such that I is less than j but pi is greater than pj, right? That is what we mean by inversion, right? So given this permutation p, find the least number of swaps that are required such that the resulting permutation only has one inversion. So that is the problem. Now how can we solve this? So let's move on to the solution. The very core idea or the argument that we need to solve this problem is that every permutation can be seen as a group of directed disconnect cycles, right? So let me write it down because it can be a lot to absorb. So what I mean is every permutation is just a group of directed disconnected cycles, right? And there is a very good video on this on YouTube. I would highly recommend you guys to go and watch that, but still I will give you guys a brief overview what I mean by this. So let's take a small example to explain this. Let's say I take the example of 2, 3, 1, 5 and 4, right? Let's say you want to sort this. So I want my element 1 on the first index, I want my element 2 on the second index, third on the third index, fourth and fifth, right? So something like this. So I want my element 1 on the first index, so I can kind of draw an edge from 1 to 2, right? So I can draw an edge from 1 to 2. Similarly, I want my element 2 on the second index, so I can draw an edge from 2 to 3. So I can draw this edge. Similarly, I can draw an edge from 3 to 1, I can draw an edge from 4 to 5, and I can draw an edge from 5 to 4. So as you can see, now I have broken down my permutation into group of cycles, right? So I have two cycles here. I have 1 to 2 to 3, right, and 3 to 1. Then I have 4 to 5 and then 5 to 4. Basically my permutation 2, 3, 1, 5, 4 is equivalent to these two cycles, right? They are basically the same thing. Now like how is this useful? So like if you want to count the number of swaps that are required to sort the permutation, it will be just equal to number of swaps required to sort will be equal to n minus number of cycles, right? So in this case n is equal to 5 and number of cycles is equal to 2, so my answer will be 3 swaps. So I will require 3 swaps to solve, or you can say sort, this permutation. But how is this useful to us? Like this can be used to achieve any state in the permutation, right? Like in this case we are just sorting, but let's say you don't want to sort the permutation. Let's say you have been given 2, 3, 1, 5 and 4, and let's say you want to convert this to a permutation of 2, 1, 3, 4 and 5, right? So now you are not sorting it anymore, now you are making some other permutation, right? So here you have an edge from 2 to 2. So there is a kind of a self loop here. Then we have like a edge from 1 to 3. So we draw this edge, then we draw an edge from 3 to 1. Then I draw an edge from 4 to 5, and then I draw an edge from 5 to 4. Now in this case, we have 3 cycles, right? So we get 2. This is a self cycle. Then we get a cycle from 1 to 3 and 3 to 1. Then I get a cycle from 4 to 5 and 5 to 4, right? So if you count the number of swaps that are required to make this permutation into 2, 1, 3, 4, 5, it is equal to n minus number of cycles, and that will be just 5 minus 3, that is equal to 2. So we just require 2 swaps to make this permutation to 2, 1, 3, 4, 5. Or you can say basically this is the target permutation, right? You can say this is the target permutation. And if you observe one more thing here, you can see that your target permutation in this case only has one inversion, right? So I hope like you are able to see the idea behind this, right? Why we are like breaking down the problem into cycles. So this is not only useful to find the number of swaps to sort the array, it can be used to find the number of swaps required to get to any target permutation, right? So we have a sorted order, right? We have a sorted order that is 1, 2, 3, so on up to n, right? This has 0 inversions. Then we find the permutations with 1 inversion, right? Permutations with 1 inversion. So these will be 2, 1, 3, so on up to n. This is the permutation that we just chose, right? We chose 2, 1, 3, 4, 5 as a target here, right? So we solved for this one, right? So like we just solved for this one. Similarly, we can have 1, 3, 2, so on up to n. We can have 1, 2, 4, 3, so on up to n. And in the end, we can have 1, 2, 3, so on up to n and n minus 1, right? So you can say, so you can see that almost like entire permutation is sorted, right? 3 up to n is sorted, only 2 elements, that is 2 and 1 are different. Similarly here, entire permutation from 1 up to 3 to n is sorted, right? But only 3 and 2 are different. Similarly here, 4 and 3 are different, and in the end only n and n minus 1 are different. So like the permutations with 1 inversion are like very close to sorted order, right? They are not exactly sorted, but they are very close to sorted. So one of the solutions that you can do is, right, choose this as target, right? Choose this as target, find the number of swaps. This will take O of n time. Then change your permutation, right? Choose the second one as target and solve for this. This will also take O of n time. Then solve for third one, and so on, solve for the last one, right? So on, solve for the last one. So like if you try to set every permutation as a target and try to solve it, every permutation will take O of n time. So in total we have n minus 1 such like permutations, and every permutation takes O of n time. So it will take you O of n square time to solve this, right? If you try to do it in a naive manner. But in this case, our n is up to 10 to the power 5, so we cannot do the naive approach. So we have to do something like smart. And the smart thing here is that you can observe that like the sorted order is like very close to the permutations with 1 inversion, right? So we can somehow use the sorted order. We can somehow use the sorted order to solve for the order with 1 inversions, right? So let's take some example. So let's say we have P1, P2, P3, so on up to Pn, right? So somehow in the somewhere in the middle we will have Pi and Pi plus 1, right? We'll have 1, 2, 3, so on up to I plus 1, up to n, right? This is the sorted order. In this case, there will be an edge from 1 to P1, 2 to P2, 3 to P3, and so on, Pn to Pn, I to Pi, and I plus 1 to Pi plus 1. But let's say I choose a permutation with inversion, right? So in that case, my elements here will be P1, P2, P3, so on up to Pi, Pi plus 1, so on up to Pn, right? 1, 2, 3. But here I will not have I and I plus 1. Here my I plus 1 and I will be swapped, right? Because I am choosing a permutation with 1 inversion. So here I will have I plus 1 and here I will have I. So here I will get let's say n, right? So this was a sorted order and this was a permutation with only one inversion. So all the edges will remain same, right? There will be edge from 1 to p1, 2 to p2, 3 to p3 and n to pn. But now there's an edge from I plus 1 to pi and I to pi plus 1, right? So like in every permutation we are breaking two edges and we are adding two new edges, right? So like we have to somehow use this fact to answer the problem. Now how can we use this? So let's first find the cycles in the sorted order, right? Let's first try to solve this problem and try to find the cycles in this one. Try to find the cycles in this one. There are two cases. I can break the problem down into two cases. The first case is my pi and pi plus 1 lie in the same cycle, right? So I will have something like this. Let's say you form some cycles, right? Let's say there's a cycle 1 here. Let's say I have some other cycle here. This is, let's say, cycle 2, and then we have a cycle that has pi, right? There's an edge from I to pi, and somewhere it has a edge from I plus 1 to pi plus 1, right? So let's say this is a cycle 3rd. So this is equivalent to the sorted order, right? This is equivalent to the sorted order. So like this is the cyclic representation of the sorted order. So in this case my pi and pi plus 1 are in the same cycle. So now I am breaking the edge from I to pi plus 1, right? I am breaking the edge that goes from I to pi plus 1. I am breaking this. Similarly, I am breaking the edge that goes from I to pi, that goes from I plus 1 to pi plus 1. So I am breaking this edge. Now I am adding a edge from I plus 1 to pi, right? I am adding edge from I plus 1 to pi, something like this. Similarly, I am adding an edge from I to pi plus 1, right? So you can see that initially I had 3 cycles, but after I broke the edges, it created a new cycle, right? Now I have a 4th cycle. This is cycle 4. So like you can like see the observation here. If your pi and pi plus 1 lie in the same cycle, then after you break the edges or after you invert them, your like inverted order will have number of cycles plus 1, right? Number of cycles plus 1. So you don't have to recompute the number of cycles, right? You can just see the cycles in the sorted order. Then you can check if pi and pi plus 1 are lying in the same cycle or not. To check this, you can use a DSU. To check this, we can use a DSU. And if they are lying in the same cycle, then after you break them apart, right, there will be a new cycle. So the number of cycles will increase by 1. That is the case when pi and pi plus 1 are lying in the same cycle. Let's see the case when they are not. So let's say pi and pi plus 1 are not in the same cycle. So we have something like this. We have I, the edge goes to pi, let's say. This is, let's say, cycle 1. Then we have some other cycle here, right? Let's say this is cycle 2. We don't care about this. Then let's say this is a 3rd cycle. And there is an edge going from I plus 1 to, let's say, pi plus 1. Right? So something like this. Now we break the edge from I to pi plus 1, right? I break this and I break this I plus 1 to pi plus 1. Then I add an edge from I to pi plus 1 and I add an edge from I plus 1 to pi. So now as you can see, in this case, my 2 cycles are merging, right? So this is the opposite case. So if my pi and pi plus 1 are lying in different cycles, then my cycles will merge, right? Then you can see the new number of cycles in inverted order my number of cycles will be cycles minus 1, right? So now you don't need to recompute again and again. Now we can just use a sorted order to find the number of cycles in the inverted order, right? So that is the entire solution. So let me write the pseudocode or algorithm that you can use to solve this. So first of all, create a DSU of n nodes that will store my cycles. So for every element, for every pi, create a edge from I to pi, right? Create number of you can create cycles. So for every pi, create a edge from I to pi. This will be your sorted order. This will be your sorted order. And count the number of cycles. Count the number of cycles in sorted order, right? Then we need to find the number of cycles in every inverted order, right? So to do that, for every I which goes from 2 to n, check if pi and pi minus 1, or we can do this in reverse order. Let's say I go from 1 to n minus 1 and check if pi and pi plus 1 are in same cycle or not, right? If they are in the same cycle, then answer is equal to minimum of answer n minus cycles plus 1, right? Because when you break the elements in same cycle, the number of cycles will increase by 1. So in this case, your answer will be n minus cycles plus 1, right? So you can say your answer is equal to minimum of answer and n minus cycles plus 1. Otherwise, if they are from different cycle, your answer will be answer is equal to minimum of answer and n minus cycles minus 1, right? And in the end, you can just print out your answer, right? So that is the logic that you guys can use to solve this. If you guys have some doubts, feel free to ask them in the comments or their Discord server. I'll be more than happy to answer them. Now let's move on to the code and see the code. So here's the code. I can keep a DSU. I will create an edge for every I from I to vi, right? Then I will count the number of cycles. So I first of all, I create a sorted order. Then I find the number of cycles that are required, that are in that sorted order, right? Then I will go for every I from 1 to n minus 1, and I will check if my two elements pi and pi plus 1 are in the same cycle or not. If they are in the same cycle, then my answer will be n minus cycles plus 1. Otherwise, my answer will be n minus cycles minus 1, right? So that will be the entire solution. What I mean is that you guys don't need to check for this every time, right? Because you only have two possible answers. You have only two possible answers. Either it is n minus cycles minus 1 or it will be n minus cycles plus 1. Obviously this one is smaller, right? This one is smaller. So if you find some value of I such that the answer is n minus cycles plus 1, then you can just print this and you can exit. Just print this and exit. Otherwise, if you check for all the index and you are not able to find this answer, then the answer is obviously this, right? That is the same approach. So that is it, and I will see you guys in the next one. Bye bye.